Okay, so the next chunk of this lecture is going to be that both intake and output of water is regulated. So this is just a diagram of the average intake per day and the average output per day. Your intake of water per day is about 60% of the beverages that you drink, 30% from the foods that we eat, and then 10%, which is not much, but there is a 10% through metabolism, which we call metabolic water. So 10% is going to be considered metabolic water. And one thing to note or to make sure you pay attention to is that input is relatively equal to output of water in order to remain hydrated. So the amount that we're bringing in, we're also excreting out in order to stay balanced. And that's about 2,500 milliliters per day or 2.5 liters of water or fluid a day, which equates to about 84.5 ounces. Our output of water is going to be things like feces. We lose some water in our feces, some in our sweat, mostly urine. And then there's this little category over here called insensible loss. So insensible loss over here is going to be basically immeasurable loss. So the fluid that we lose via our skin through evaporation and through our lungs, that's not measurable. We can't capture that fluid loss. So immeasurable. And so is that how you spell that? Immeasurable? Let me double check. Immeasurable. Yes, okay, I was right. That's immeasurable. All of the other ones, the sweat and the feces and the urines, those would be considered sensible losses that are considered measurable, that we can measure those things. So immeasurable is the insensible loss that we lose through our skin and lungs, which we cannot measure. Okay. If we have a decrease or increase in osmolality, that is going to trigger a homeostatic feedback mechanism. I'm going to erase some of this so I can write that down. So increase and decrease in osmolality will trigger homeostatic feedback. So if we have an increase in osmolality, so we have our osmolality is increased or more concentrated and more solutes, and what's going to happen is that's going to trigger our thirst mechanism. And we'll talk more about that in a second. And triggers ADH release. Both of these things will cause us, not thirsty, but I should say thirst. So if I just cover it with a T, I hope so. You know what I mean. You know it should be tea thirst. Yeah, it doesn't work, but just know it's thirst. So if we have an increase in osmolality, our body's too concentrated, then that's going to trigger thirst. So we're going to bring in more water to dilute that osmolality, to decrease that osmolality so we're not so concentrated. Also will trigger ADH release, which ADH release is going to cause more aquaporins to be put in the collecting duct of our urinary tract, in order for, so after the nephron, we have that collecting duct where all the nephrons kind of feed into, but we're going to add more aquaporins in that collecting duct in order to reabsorb more water into the blood, which should decrease that osmolality as well. If we have a decrease in osmolality, so everything's just too diluted, then we're going to inhibit thirst so that we're not drinking any more water, and we're going to inhibit ADH release so we're not reabsorbing any extra water. So a decrease in osmolality is just going to inhibit those mechanisms. Okay, and one thing to know is that, and I've mentioned this before, sodium and water are very, very closely tied. Wherever sodium goes, water goes, which is why when we have release of aldosterone and we reabsorb more water, water follows, so we get an increase in blood volume and therefore an increase in blood pressure. So make sure you know that sodium and water are very, very, very closely tied. Okay. So then next we're going to talk about the thirst mechanism. All right, so which kind of receptor detects changes in osmolality? It's called an osmoreceptor. And the way that an osmoreceptor works is that it's going to, and this is already in your lecture notes, so you can just follow along, is that it's going to detect plasma membrane stretch. So how we detect osmolality is by how much water it is and how much it stretches our cells. And so that plasma membrane stretch will tell us of any losses or gains of water, which is indirectly going to tell us about osmolality. More water and more stretch means less osmolality, less water, less stretch, more osmolality, or more concentration. And it doesn't really take much much change. A 1 to 2% increase in osmolality will trigger these osmoreceptors. So it doesn't take much change in order to get these homeostatic feedback mechanisms to turn on. So if we have an increase in osmolality, more than a 1 to 2% increase in osmolality, or equal to, that triggers these osmoreceptors, what is going to happen? It's going to trigger a couple of different things. It can trigger dry mouth, which we've talked about before. Let's see, do you remember what it's called? I'll give you a second to think about what it's called before I write it down. It's called xerostomia. So xerostomia is dry mouth. So if we have an increase in osmolality, which means that our blood is too concentrated, our body is too concentrated, we are going to have dry mouth, which is part of the thirst mechanism. So that kind of cues us to drink more water so that we can absorb more water and therefore decrease that osmolality. And so the way that xerostomia works, or dry mouth works, is that so dry mouth or xerostomia by reducing salivary gland secretion. So less saliva, dry mouth, and it should cue us to drink some water. Okay, this thirst mechanism is triggered by the hypothalamus, and I believe that is already in your lecture notes. Yes, so the osmoreceptors in the hypothalamus detect this decrease or increase in osmolality, which is going to trigger that dry mouth if we have an increase in osmolality, meaning our body's too concentrated, so that we bring in more water and therefore dilute that concentration. Another way that the thirst mechanism is triggered is if we have a blood volume decrease. So we're lacking water in our blood. And so with blood volume decrease, and I don't know if this is actually on this slide or not. Let's see. No, it's not. Okay, so I'm going to write this down. When we have a blood volume decrease, anytime we have a blood volume decrease, well, I guess that's already written there, but blood volume decrease also means a blood pressure decrease. And so if we lose blood volume by 5 to 10%, like in the case of like a hemorrhage, okay, that is going to trigger our baroreceptors, which detect pressure, which, and I'll put 5 to 10% decrease. Our baroreceptors, which detect pressure, are going to detect that, which is going to trigger that RAA pathway that we've talked about before, the renin, angiotensin, aldosterone pathway. So we're going to have release of aldosterone, ADH, that thirst mechanism we just talked about, and some vasoconstriction in order to get that blood pressure back up. Okay, so all part of the thirst mechanism. But again, because the thirst mechanism is part of that RAA pathway, other things are going to be working together to make that blood pressure go back up. Okay, another kind of review question. What is the excessive thirst in patients that we may see with blood loss or an increase in osmolality, or like in the case of diabetes mellitus. What is the name of that excessive thirst that you should have learned about in your critical thinking assignment? It's called polydipsia. So polydipsia is excessive thirst. So make sure you remember that. All right, next is a diagram based on this thirst mechanism here. So if we have an increase in osmolality, then that means that our osmoreceptors in our hypothalamus, like we just said, is going to detect that. We're going to have a decrease in saliva and dry mouth. So all of this is going to start that hypothalamic thirst center, which gives you that sensation to drink. You have a dry mouth and you have this thirst mechanism, and you're going to want to drink more water. And so hopefully the individual drinks some water, which moistens the mouth, the throat, stretches the stomach and intestines. More water is absorbed from our GI tract, which should decrease the osmolality back to normal and bring our plasma volume up as well as a result. Now, if this mechanism is triggered not by osmolality, but by a decrease in plasma volume by 5 to 10%, now again, that's also going to decrease our blood pressure. Anytime we lose blood volume, we're going to drop our blood pressure, which our granular cells in our kidneys are going to detect that. It's going to release renin, which that renin is going to convert angiotensinogen into angiotensin 1. Then the ACE enzyme from the lungs is going to turn angiotensin 1 into angiotensin 2. If I'm moving too fast for you with that, go back, review the RA pathway that we talked about during blood vessels and we talked about during the urinary system. But that angiotensin 2, part of that multi-step pathway, part of that pathway is to trigger that thirst center so that we feel thirsty, get that sensation to drink water, and then we can reabsorb, or not reabsorb, but absorb more water through our GI tract and therefore bring up our plasma volume and therefore our blood pressure back up to normal. So that should be review. We've talked about this before, so just make sure that you're still reviewing that information and have that ready for you on the final. So regulation of water output, obligatory water losses. So there are a certain amount of water that we must lose that we just talked about with that very first diagram. We lose water through our feces, we lose water through our sweat, we lose water through our urine. Those are sensible losses that can be measured, as well as the insensible losses that we lose through our skin and our lungs. So all of that is considered obligatory losses. Beyond that, the amount of fluid that we output is going to depend on how much we intake. So are we bringing in extra water and therefore outputting extra water? Is our diet high in water? So are you vegetables have a lot of water content, and so are you eating lots of food that have high water content and therefore bringing in more water and therefore getting rid of more water? Or did you lose water? Did you have some kind of water loss, maybe through diarrhea or vomiting, and so you're actually outputting less water than you normally would because of that water loss that you experienced? And know that water loss is pretty balanced. So if you're sweating more and you're losing water that way, you'll typically tend to urinate less because you're already losing more water through your sweat. Okay, and I think all of that is in your lecture notes. Let me double check. Yes, all that is in your lecture notes. There is a 30-minute delay in eliminating excess water. So it takes about 30 minutes for us to inhibit that ADH. So if we're drinking in excess water, so let's say I just got a big old jug of water and I drink a whole lot of it, it takes about 30 minutes for us to delay that. There's a 30-minute delay in inhibiting ADH, because ADH is going to be reabsorbing more water through our urinary system. And if we're drinking excess water, we really don't want to be reabsorbing too much extra water and diluting our blood. And so it takes about 30-minute delay for us to have that ADH inhibition. And then when we do have that ADH inhibition, because we've taken in excess water, then we're going to urinate some more in regards to that, or in response to that. So drinking a bunch of extra water takes about a 30-minute time frame for us to inhibit that ADH release, which will cause us again to urinate more. It takes about 30 minutes. So we see this here. If we have an increase in osmolality, so we're more concentrated, or have a high concentration of sodium in our blood plasma, and then so this is going to trigger our osmoreceptors in the hypothalamus because if we're too concentrated, we're going to need to put more water into the blood and blood plasma to kind of balance that out. So if we're too concentrated, high ECF osmolality, osmoreceptors in the hypothalamus will detect that. It's going to cause the posterior pituitary to release more ADH. That ADH will make sure that the ADH will make sure that there are more aquaporins in the collecting duct of the kidneys, which causes more water reabsorption, which should bring down that osmolality from where we started. Also, if you're experiencing a decrease in plasma volume, so you lose some water, and therefore your blood pressure goes down, you have baroreceptors in your atria and your carotids that are going to then trigger again the posterior pituitary to release more ADH, put more aquaporins in the collecting duct, so we have more water reabsorption and therefore a higher plasma volume. But know that anytime we are reabsorbing more water, which decreases our osmolality and increases our plasma volume, anytime we put more water into the blood, we're now going to have less of a urine volume or urine output because more of that water is being redirected towards the blood. So again, that REA pathway, if you have not reviewed it in a little bit, make sure that you do review it. We do have baroreceptors that are going to detect drops in pressure, which is going to increase our sympathetic nervous system activity, which causes that renin to be released from the kidneys. That renin is going to convert angiotensinogen into angiotensin 1. We have an angiotensin converting enzyme from the lungs that turns angiotensin 1 into angiotensin 2. That triggers all four of these pathways. Remember that vasoconstriction is a short-term response so that we can vasoconstrict our blood vessels to bring up that blood pressure temporarily. But on the long term, we're going to have an increase in thirst so that we bring in more water and therefore we absorb more water to bring up our blood volume. And then we'll have both ADH and aldosterone release. Aldosterone causes sodium reabsorption and water follows. ADH causes water reabsorption. Both of those, again, cause water reabsorption, which is going to bring up blood volume and therefore increase blood pressure. So if you haven't reviewed that, make sure that you do. All right, disorders of water balance. And how much did we talk there? I guess a good amount. I guess I can maybe, no, it's only one slide. We'll talk about the whole thing. Okay. We're talking about dehydration, hypotonic hydration, and then we'll talk a little bit about edema. So we'll talk about dehydration first, which is at the very top here. This person, and again, I always say for whatever reason, I don't know why they use example, but there is this woman here. She is running through the desert, which I expect is very, very hot. It causes her to sweat a lot. So then we have this excessive loss of water from the ECF, from our extracellular fluid, because we're sweating. So now we're excreting all of this water, which means that the ECF inside of our body, like our blood plasma and our interstitial space, is going to be losing water and therefore have a increase in osmolality. And if we have that increase in osmolality at the higher concentration outside of our cells, hypertonic solution, that water is going to move toward the higher concentration, and therefore those cells are going to shrink. And so this happens not only when someone is running through the desert, but also we may get this with people, like we just said, with sweat, if you're running through the desert, or hemorrhage. So losing lots of blood. Burns cause you to lose lots of fluid. Excessive vomiting or emesis we talked about before. Diarrhea also causes a lot of fluid loss. Let's see, diuretic abuse, we talked about that as well. If you use diuretics and you're urinating more often than you should, then you're losing excess water. And then if you are if you have a very low water intake, all of these things will cause us to lose more water than we should, and therefore cause our cells to lose water to that extracellular fluid because it's more concentrated. And therefore our cells will shrink and it makes it harder for our cells to work that way. And so people will then experience symptoms that are like hypovolemic shock that we talked about with blood. So make sure you go back and review hypovolemic shock because they would experience the same symptoms here. So So that's that. That is dehydration. Hypotonic hydration. Hypotonic hydration is when you're intaking too much water. So there's this girl who's drinking 6 cups of water. It looks like she just finished 5 and she's on her 6th cup here and she has a jug of water right next to her. Anytime you bring in too much water, now you're diluting your extracellular fluid. So you're diluting your blood plasma, diluting the interstitial space or interstitial fluid. And now your cells are in a hypotonic solution. Now the concentration outside the cell is less than the concentration inside the cell. And therefore, this is going to cause a fluid shift and cause water to move into those cells because now inside the cell is more concentrated than outside because you just diluted all the outside of your cells from drinking that excess water. And so because the cells are in a hypotonic solution, hypo makes a hippo, and that water is going to shift to inside the cell to try to dilute the inside of the cell. And those cells are going to swell. And if it's too much of a difference in gradient, and too much of a difference in concentration, then those cells could eventually burst. Now, one of the more serious complications of overhydration is something we call hyponatremia. So we'll learn about it in a second, but over 90%, I think it's 98%. Pretty sure it's like 98%. Let me double, no, about 90, sorry, too much, but 90, about over 90%, about 90% of our fluid in the extracellular fluid is going to be made up of sodium. So about 90% of our solutes in the extracellular fluid compartment is sodium. So we need sodium. We need lots of sodium available. And so if we are overhydrating and bringing in too much water, that can cause hyponatremia, where our cells don't have enough access to that sodium. And so with hyponatremia, too little sodium, this leads to nausea, vomiting, muscle cramps. You know that sodium is super, super important. And that high concentration of sodium on the outside of the cell is super, super important for the depolarization of cells, that rapid depolarization phase to allow for the action potential to continue up until positive 30 maximum. So muscle cramps. And then also can cause cerebral edema, so swelling in the brain. And if it gets to that point, it can then lead to disorientation, convulsions, coma, or even death. And so the way that we would treat this, we would treat with a hypertonic saline solution. Saline meaning sodium. So we just give them more sodium. We give them what they lack to help deal with these symptoms and get them back into homeostasis when it comes to sodium. That's hyponatremia. We'll bring it up again here in a second. Let me erase this stuff. So if you still need to pause, write it down, but I'm going to go ahead and delete it. Okay, so the next thing is something we've already talked about, which is edema. And edema, as you already know, is fluid in that interstitial space. All right. So with edema, when we're talking about just straight edema, we're talking about fluid in the interstitial fluid only. Okay, we're not talking about third spacing. We're just talking about extra fluid in our interstitial fluid compartment, also known as tissue edema. And so when we have that edema in the interstitial space, that increases the distance, and I believe this is already in your lecture notes, but it increases the distance required for oxygen and nutrients. So if we're trying to get oxygen and nutrients from our blood plasma into our cells, and we're experiencing edema, well, we have all this fluid in that middle space, in that middle compartment. And so it's going to increase the amount of distance that oxygen and nutrients need to travel in order to get to inside the cells, to get into that intracellular space. And so it just puts more pressure on the body. We have less of delivery of the oxygen nutrients because it's just taking so much more time because of all the fluid that it has to pass through in order to get into the cells. Okay, so that's complications of edema. Okay, and then I'll stop the recording there, and then the next part is going to be balance of different solutes.